Assalamu alaikum. Our project is Driver Assistant. My group members are Asma Maqsood, Sabeen Mustafa, Mehrunisa Khalid, and Shafaq Mehboob. Since last evaluation, we do speech recognition learning. Speech is a complex phenomenon. People rarely understand how is it produced and perceived. Speech is a dynamic process without clearly distinguished parts. It's always useful to get a sound editor and look into the recording of the speech and listen to it. Here is, for example, the speech recording in an audio editor. Structure of speech. Speech is a continuous audio stream where rather stable states mix with dynamically changed states. In this sequence of states, one can define more or less similar classes of sounds or phones. Words are understood to be built of phones, but this is certainly not true. The acoustic properties of a waveform, pressure and time corresponding to a phone can vary greatly depending on many factors, that is phone context, speaker, style of speech, and so on. The so-called coarticulation, the articulation of two or more speech sounds together so that one influences the other, makes phones sound very different from their canonical representation. Next, since transitions between words are more informative than stable regions, developers often talk about diphones, parts of phones between two consecutive phones. Sometimes developers talk about subphonetic units. Different substates of a phone, often three or more regions of a different nature, can be found. Sometimes phones are considered in context. Such phones in context are called triphones or even quinphones. For example, A with left phone B and right phone D in the word bad sounds a bit different than the same phone A with left phone B and right phone N in the word ban. Please note that they are matched with the same range in waveform as just phones. They just differ by name because they describe slightly different sounds. For computational purpose, it is helpful to detect parts of triphones instead of triphones as a whole. The whole variety of sound detectors can be represented by a small amount of distinct short sound detectors. We call those detectors xenons. A xenon's dependence on context can be more complex than just the left and right context. Phones build subword units like syllables. Sometimes syllables are defined as reduction stable entities. Subwords form words. Words are important in speech recognition because they restrict combinations of phones significantly. Recognition process. The common way to recognize speech is the following. We take a waveform, split it at utterances by silences, and then try to recognize what's being said in each utterance. To do that, we want to take all possible combinations of words and try to match them with the audio. We choose the best matching combination. First is feature vector. Since the number of parameters is large, we are trying to optimize it. Numbers that are calculated from speech, usually by dividing the speech into frames. Then for each frame, typically of 10 milliseconds length, we extract 39 numbers that represent the speech. That's called a feature vector. Second one is model. A model describes some mathematical objects that gather common attributes of the spoken word. In practice, for an audio model of xenon, it is the Gaussian mixture of its three states. To put it simple, it's the most probable feature vector. The model of speech for speech decoding is called Hidden Markov Model or HMM. It's a generic model that describes a black box communication channel. In this model, process is described as a sequence of states which change each other with a certain probability. Third is matching process. In matching process, we will compare all feature vectors with model and get the best matching combination. According to the speech structure, three models are used in speech recognition to do the match. An acoustic model contains acoustic properties for each sentence. A phonetic dictionary contains a mapping from words to fonts. This mapping is not very effective. For example, only 2 to 3 pronunciation variants are noted in it. A language model is used to restrict word search. It defines which word could follow previously recognized words and helps to significantly restrict the matching process by stripping words that are not probable. Those three entities are combined together in an engine to recognize speech. If you are going to apply your engine for some other language, you need to get such structures in place. Other use concepts. A lattice is a directed graph that represents variants of the recognition. Often getting the best match is not practical. In that case, lattices are good intermediate formats to represent the recognition result. And best lists of variants are like lattices, though their representation are not as dense as the lattice ones. Word confusion networks sausages are lattices where the strict order of nodes is taken from lattice edges. Speech database, a set of typical recordings. Speech databases are used to train, tune, and test the decoding system. Text databases, sample texts collected, for example, language model training. Usually, databases of texts are collected in sample text form. The issue with such a collection is to put present documents like PDFs, web pages, scans into a spoken text form. Word error rate. Let's assume we have an original text and a recognition text with a length of n words. I is the number of inserted words, D is the number of deleted words, and S represents the number of substituted words. With this, the word error rate can be calculated as by the given formula. Accuracy. It is almost the same as the word error rate, but it doesn't take insertion into account. It also calculated as by the given formula. Speed. Suppose an audio file has a recording time RT of 2 hours and the decoding took 6 hours. Then the speed is counted as 3x RT. Another problem you need to consider is the availability of speech material for training, testing, and optimizing the system. The testing set should be representative enough acoustically and in terms of the language. It might be a couple of recordings you could do yourself. For the training set and the models, you should check the resources that are already present. To build a phonetic dictionary, you can use one of the existing TTS synthesizers, which nowadays cover a lot of languages. For language models, you will have to find a lot of text for your domain. In the previous evaluation, we searched about Bluetooth and its protocols and its working. In this, we coded the Bluetooth detector module. This module detects its nearby Bluetooth devices and connect and paired with them using intent object. This module gets permission for turning on and off the Bluetooth of our device. Then it scans the near devices and connects with them. This module also shows the list of paired or connected devices in the list view. Syntax to detect devices is given below. This module also uses broadcast receiver. Here is the demo of the Bluetooth detector module. We also searched about text to speech. Android allows you convert your text into voice. Not only you can convert it, but it also allows you to speak text in variety of different languages. For this purpose, Android gave text-to-speech class. We need to instantiate an object of this class and also specify the init listener. Its syntax is given below. Language can be set by calling setLanguage method. Once you have set the language, you can call speak method of the class to speak that text. Its syntax is given below. Here we made a small app to check it, which converts text into speech and also show text in Toast. Here is the demo of text to speech app. We also do call receiving without voice command. For call receiving module, read phone state permission is required. Broadcast receiver and telephony manager is used for receiving call. Incoming call state message is shown using Toast when phone is ringing. If user receives the call, then call received state message is shown using Toast. Call idle state show when user ends the call or rejects the call. Here is the demo of call receiving module. We also designed our experiment scenario for our AHFE 2018 research paper. Here, the scenario shows the car falling event was occurred along urban roads where the speed limit was 40 km per hour. When the driven vehicle, that is black car in our case, stops at the signalized intersection 11, two pre-programmed lead vehicles that shows in as grey cars appear on the two lanes of road section 12. Lane 1 and 4 was blocked by parked vehicles. When the spacing between the subject and the lead vehicle reached 60 meters, the speed of the both lead vehicles increased up to 20 km per hour. When the spacing was 30 meters or less, lead vehicles increased the speed to 35 km per hour and maintained that speed. The signal at intersection 13 was kept green to provide uninterrupted flow from section 12 to 14. That's end. Allah Hafiz.